In this installment, we're going to look at collisions at a large scale. So in a collision, what happens is we have two bodies moving toward each other and they collide. But there is two possible outcomes. One of those outcomes is that they stick together and move off together. The other possibility is that they bounce off each other. So we could informally call these sticky or bouncy collisions. Now, the scientific technical name for these are elastic and inelastic. And what is true in those two cases is that in inelastic collisions, the kinetic energy does not remain the same. In elastic collisions, the kinetic energy does remain the same. So whenever we have a sticky collision, we would expect that the kinetic energy will not be the same before and after. In the case where they bounce, we would expect that kinetic energy would be the same before and after the collision. Let's look at a little bit of algebra now for elastic collisions. We know the law that governs all of this is the law of conservation of momentum. Is that the momentum before an event is equal to the momentum at any instant after the event. So if we have two bodies that are going to come together and bounce off, well, we have the momentum of, let's say, call it 1 and 2. So we have the momentum of 1 plus momentum of 2 must be equal to the momentum of 1 and 2 afterward. But P1 and P1 can't be the same, nor can P2 and P2 be the same. Well, they might be the same. But we need to name them differently. And the convention we do this is we put a prime. That little symbol is a prime. It's an apostrophe. And that's the way, when necessary, we designate something before and something after. So this is the expression that we use for determining what goes on with a bouncy collision. Now, we can extend this. We could expand this to be P1 plus P2 plus P ... any number of P's. So P1 plus P2 prime, P2 prime plus P3, P3 prime, and we could keep adding more and more if we want. So our basic approach is to determine the number of particles beforehand and the number of particles afterward, and we create a momentum term for each of those. And so that's what our expression looks like. When we get to inelastic collisions, there's a difference. And the inelastic collisions, we start out with our law of conservation of momentum, perhaps the most important rule or law in all of physics, certainly in AP Physics 1. Well, we have two bodies coming together, P1 plus P2. And afterward, we have this new body, which is this new particle, P12. So we have a term for this particle, the first particle, the second particle, and a term for the particle afterward. Now, since this is combined, we know P12 is not P2, nor is it P1. So we don't need to use primes. But we want to go a little bit further to show something of great importance in looking at this. Is that the momentum of 1 is m1 v1. And the momentum of 2 is m2 v2. The momentum of 1, 2 is the mass of 1, 2, and the v. We don't need to put to specify because that v, there's only one v on that side. But what is interesting is that when we look at this side afterward, the m12 is and can be expressed as m1 plus m2v, which is important because if we want to find out what the velocity is or predict the velocity afterward, you can see that these two terms will drop out, and we are left with an expression of v equals the sum of the individual momenta beforehand divided by the sum of the masses of the two. So this is an overview of how we approach collision reactions, interactions.